Okay, continuing on with the lecture for sections 1.3, 1.4, and 1.5, looking at this graph, we are asked now, I'm going to look at finding f at -7, f at 1, f at 5, f at -4, f at -1, and f at 3. So really, they're asking for different y values for given x's. So remember that f of x is equal to y. So these are different x values. So we could kind of make a table. We could look at when x equals -7, 1, 5, -4, -1, and 3. Those are all the different f of x values that we're looking for, or in this case, y values. Okay, so we can just look up onto the graph at -7. Here's -3, 4, 5, 6, 7. When x is -7, y is 1, 2, 3, 4. So here's the coordinate -7, 4. And so that tells us when x is -7, y is 4. When x is 1, y is 1, 2, 3, 4, 5. When x is 5, y is 2. When x is -4, y is 4. When x is -1, y is 1, 2, 3, 4, 5, 6, 7. And finally, when x is 3, y is also 3. So it's pretty easy to find the y values when you're given particular x values. Now, it's a little bit trickier on this problem to go the other way because we want to solve the equation f of x equals 3. So this is the equation that we're looking at, or the problem that we're looking at right now. And so what that's asking is, what are different x values, or what are the x values when y is 3? And so if you look at what you want to do is imagine when y is 3. So I'm going to try and draw a horizontal line for when y is 3 here. These are all the, sorry, it's not, my pen doesn't do very well. But that's when y is 3, so we want to give these different x values. So we need this point, this coordinate, and then all of these values. So some of these are going to be actually easy to find. Obviously, when y is 3, x is 3, so we have one answer at 3, 3. Now, let's see here. This is 4, 5, 6, 7, 8, 9, 10, 11, 12. When x is 12, or actually any number greater than 12, y gives you get a y value of 3. So we know those solutions for sure, but we need to find this point and this point. And you can kind of estimate them, but that's not what they want. They want the exact value. And because we have a straight line going between this point, we can find the equation of this line and set that equation equal to 3, and that will give us exactly the x value for when this line is equal to 3. So this is good because it'll help us review. And then we'll have to do the same thing for this problem. So let's remember a line when it's made up of 2 points, we want to a line is defined by 2 points. We want to find the slope of that line and then write the equation. So this is the coordinate -3, 0 right here. And then this is the coordinate, let's see, 1, 2, 3, 4, -4, positive 4. -4, positive 4. So you can find the slope just by counting or using the formula change in y over change in x. But this is 1, 2, 3, 4 over 1. So this is a slope of -4. If you did 4 minus 0 over -4 minus -3, you would get the same thing of -4. So we know the slope of the line is -4. And then we have the equation, the point slope equation for a line y minus y1 equals m onto x minus x1. And we'll just choose the point -3, 0 because that's easy. So we're going to use the point -3, 0. Anytime you have a point with 0 in it, that's the one you want to use. So this is going to be then y minus 0 is equal to -4 times x minus -3. So you get y is equal to -4x minus 12. So that's the equation of that line that includes the point. So if we want to know when f of x equals 3, that's just saying what is the value of x when y equals 3. So if we put 3 in to this equation, we will get -4x minus 12. We'll add 12 to both sides, and we'll get 15 is equal to -4x. And so then 15 over 4, or -15/4, is your x value when y equals 3. So that's one solution. So that is this point right here is -15/4, comma 3. We'll have to do the same thing to get this point. 1, 2, 3, 4, 5, 6, 7, and then this is -1. So this is the point right here, -1, 7. So we'll need to find the equation of the line from -3, 0 to -1, 7 using the same method. You can see that the slope here is going to be 1, 2, 3, 4, 5, 6, 7, and then right 1, 2. So up 7 over 2, or a slope of 7/2. And then we'll come in here and find the equation of the line. So when we have a slope equal to 7/2, and this time it's positive because that's an uphill line, still using the same point, -3, 0, because that's easy. The equation for that line is going to be y minus y1, which will be 0 here, equals 7/2 onto x minus -3. So this is y equals 7/2 x plus, all right, when you distribute through here, when you multiply fractions, you just multiply top and bottom. So we put that 3 as 3 over 1. So this is going to be 21/2. Okay, and now we're going to see what value of x makes this equation 3. So we put 3 in for y, and we say 7/2 x plus 21/2. In order to solve this, we'll subtract 21/2 from both sides. So you're going to do, let's see, 21/2 minus, or 3 minus 21/2 is equal to 7/2 x. So when you want to do this type of subtraction, you're going to have to get a common denominator here. So we'll think of this as 6 over 2, because we multiply by 2 over 2. So it's going to be 6 over 2 minus 21 over 2, which is then 6 minus 21 all over 2, which is -15 over 2, is equal to 7/2. And then in order to solve for x, we will multiply. You can divide by 7/2. That's the same as multiplying by the reciprocal, which is 2/7. That's how we would solve for x there. And then the 2's cancel, and so you get x equals -15/7. So this problem was a little bit tricky, but it got you remembering how to write an equation for a line and such. So you actually have 3 solutions, or well, actually infinitely many solutions. We have a solution, so f of x equals 3 when x equals -15/4, -15/7, and then back on the graph we were able to find it at exactly when x was 3 and when x was greater than or equal to 12. So when x equals 3 and when x is x greater than or equal to 12. Okay, now let's look at the next problem. It says a closed box with a square base of x inches is to hold 64 cubic inches. Write the surface area of the box as a function of x. This is a pretty classic problem. The box has a square base, and it's a closed box, so it has a lid. All right, so maybe your picture looks a little better than mine. I don't know. All right, so this is x by x. We don't know the height of the box. We're not told. What are we told? Just that it has a square base. So the volume of a box is length times width times height. We know the volume in terms of the what we're just letting the base and the length are both x times the height. So it's going to be x times h, or x squared times h. We know that that's equal to 64 inches cubed. Now, how would we describe the surface area? Well, there are a top and a bottom. There is a top and a bottom to this box, and then we have 4 sides. The top and the bottom have surface area of just base, or length times width, x times x. So we have 2 x squareds, because one for the top and one for the bottom. Now, what about the sides? Well, you have 4 sides, and they each have an area of x by h. So you have 4x times h. Now, the problem asks you to write the surface area as a function of x. So the problem is, in this equation that we've come up with for our surface area, we have an h in it. So we need to solve this equation, this volume equation for h, and then use that information to plug it in to describe the surface area in terms of just the letter x. So you should see then that this is easy enough to solve. H is equal to 64 divided by x squared. So it is this 64 divided by x squared which is going to replace h in your surface area equation to get the function. So the surface area in terms of x, we can use that function notation there, is equal to 2x squared plus 4x times 64 divided by x squared. And we can clean this up a little bit. This is going to be 2x squared. The x's cancel, and we'll have 1 in the bottom. 4 times 64 is 256. So this is 256 divided by x. So that's all they want on this problem, is just the equation as a function of the surface area as a function of x. So they're just looking for this equation right here. That's your surface area in terms of x. Okay, let's continue on then. Okay, so we're moving on to these, what we call a library of functions. You should have these in your notes. These are basic functions. We've got the constant function, and you have your domains and ranges under here. The identity function is just the line y equals x. The squaring function, which is f of x equals x squared. We have the cubic function, which is this kind of little S shape. Sometimes it can go up and down. You have the absolute value function, which is the V shape. Notice that the range on the absolute value function is only from 0 to infinity because it doesn't take on any negative y values. The square root function has a domain from 0 to infinity and a range from 0 to infinity, and that's because it is always positive. Now, these notes about increasing and decreasing we'll talk about just a second, and we'll also talk about the symmetry in just a second of these different functions. Right, there's a cube root function that has this behavior. We have the reciprocal function, which is 1 over x, and this is what it looks. It has what's called a vertical asymptote at x equals 0, and that's because 0 is not in the domain of the function. It has a horizontal asymptote at y equals 0, and that's because you would never get 0. There's no value of x that you could plug in that will give you a function value of 0, so that it's never 0 in the range, you'll see. And then the reciprocal square function, all it does is it takes this negative part and flips it up. So these are just your basic functions. Might be good to put these on note cards so you kind of understand them. Here's our rational power functions. Often have, when it's to an odd power, they have just one arm kind of behavior. I call them one arm, or just sort of one bit. And then when it's to an even power, you'll have some symmetry there. You'll have some y-axis symmetry. Looks like a little bird or a little seagull. And then the greatest integer function is a function that, like, if you pick a number between 0 and 1, not including 1, it returns 0. So when x is 0.9, you get a y value of 0. When you pick a number between 1 and 2, not including 2, like 1.5, you always get a y value of 1. So it returns integer values. So that's why the range is only integers. Kind of an interesting function. Okay, what it means to be increasing or decreasing. It's increasing if, as you look at the function from left to right, if the x value is less than another x value, you know that the y value, the corresponding y values are going to be below as well. So it's increasing, a function that's increasing. You could just think of like y equals 2x is an increasing function. It looks something like this. As you move from left to right in the x and y, you get your y values also increase. Now, a decreasing function is kind of like the negative 2x. You could think of that function. It goes like this. As you move from left to right for increasing x's, you get the y's, f of x1 is greater than f of x2. So it's in an increasing manner. The constant if they're always the same. Now, this is a special side note. When you're specifying the intervals over which a function is increasing, decreasing, or constant, you need to use the intervals of the domain, which means x values only. Do not tell me the y values when you're telling me where the function is increasing or decreasing, not the y values, just the x values. Okay? We have this idea of a relative maximum and minimum is if you can find a location. It's just basically max and mins are like hills and valleys. So if you were to look at a function, say you had a function that looked like this, and say this was A, and say this obviously, maybe this is right here, this is, maybe that's a B. We have a max here at B, f of B, whatever the y value is. We have a max of the y value at that x value, and that is because we can find an interval where that is the highest value in that interval. And then we have a min. You can see it's kind of like a little valley at A, f of A. So that because we can find a place, we could find a region where it is actually the lowest value in that region, f of A. So, and then the value f of A is called an extreme value if if it is either a relative maximum value or a relative minimum value. So when we're looking for extreme values on functions, we want to be able to find a little area where it is definitely the highest. Like this B, f of B, is the highest value of the function in that yellow area. Now, obviously over here, the function does get larger than f of B, but we can find a range where, a domain where it's the largest value. Same here, this minimum. We can find an interval where that f of A is the smallest amount. Okay, so now we're asked to sketch the graph of f of x equals x squared and find the interval over which the function is increasing, decreasing, or constant. So you're going to want to sketch the graph by using tables of values in this class because we don't have graphing calculators. So let's just pick some negatives and some positives. And we also sort of have a sense of what this graph looks like. So that should help us. We know based on the notes above what the x squared looks like. So if you choose numbers like -2, -1, 0, 1, and 2, you're going to get a nice image of this graph. Okay, when x is -2, you get +4 when you square it. Multiply it by 5, you get 20. When x is -1, when you square it, you get 1. So you multiply by 5, you get a y value of 5. When x is 0, you get 0. And then when you put 1 in, you'll get 5. And when you put 2 in, you'll get 20. So we can make a nice graph here. And you should use a straight edge and try to make your graphs neat. I'm a little bit challenged with this pen, but I know that you can do a nicer job than I can. It's very important to make sure that your axes are carefully labeled and they look kind of about the same width apart. So this is my x-axis. Now my y-axis, because I go up to 20, I might want to count by 20s. So this will be, it's not by 20s, by 5s. 5, 10, 15, 20, just so I can be sure to get it all on there. And then you just go through and plot your points. -2, 20 is here. -1, 5 is here. 0, 0 is here. And then 1, 5, and then 2, 20. And you want to get enough points so that you're kind of, getting it to graph. And then you want to collect your dots, connect your dots like that, okay? So that's the graph of the function. Now, it is increasing from 0 to infinity. We are kind of drawing up. So we would say that it is increasing from 0 to infinity. That is the x interval that it's increasing on. We'll say that it's decreasing from negative infinity to 0. And it looks like we have a min at the coordinate 0, 0. We have what we call a absolute min in this case, because that's definitely the lowest value of the function. Now, this function that we're looking at is what we call an even function, because when you put 1 or -1 in, 2 or -2 in, you may have noticed that you get the same y value. So when you put, so let's just note that, let me spell it right, sorry. Let's just note that f of x is exactly equal to f of -x. And when that is true, we say it's an even function, and it means it has y-axis symmetry. We have a mirror image across the y-axis. So this is the notes now that we're talking about what it means to be an even function. When you put -x in and +x in, you get the same y value. Now you have an odd function if you put negative in and evaluate the function, you get exactly the opposite of what you would get if you had put +x in. So an example of an odd function is f of x equals x cubed. Just kind of notice, like f at 2 is equal to 8, 2 cubed. But when you do f at -2, you get exactly the opposite of what you would get if you put 2 in, because you get -8. So that's an example of an odd function. And it has symmetry about the origin, whereas even functions have what we call y-axis symmetry. So if you're looking at a function that's just defined as a set of points, and you want to decide whether it's even or odd, you just need to look at what the y values are compared to a number and its evil twin. So when x is 3, you get 5. When x is -3, you get +5. When x is 2, you get -2. When it's -2, you also get -2. At 1, you get 1. At -1, you get 1. At 0, you get 0. So you should see then that this is what we call an even function, because f of x is equal to f at -x. You get the same y value when you plug in the negative x, or the opposite of x. Okay, now when it's defined as an equation, as in this example, you're going to have to go ahead and determine it algebraically. What is g of -x? Well, that means plug -x in for x in these problems. So this is going to be -x divided by -x squared plus 1. Well, let's simplify this a little bit. This is -x divided by -x squared is really just x squared plus 1. Now, when you have this negative in the numerator like that, you can actually sort of factor it out and think of it as the opposite of this entire thing, x over x squared plus 1. But what was this? That was just g of x, right? Because that's what you started with. So you ended up with the opposite of g of x. So you started with g of -x, and you ended up with the opposite of g of x, and that is the definition of an odd function. So you got exactly opposite of the function, so you know that you have an odd function. Okay, now on these problems, we're going to decide whether we'll go through a process of the domain, the range, the intercepts, the intervals on which the function is increasing, decreasing, etc. Okay, so the domain of this function is the x values. So the smallest x value is -2, and the largest x value is So the -2 to the largest x value, which is 6. The range of this function is -3 to 2. The lowest y value, which is -3, to the highest y value, which is 2. Okay. Now, the next thing, why don't we, while we're looking at it, we can go ahead and fill it out for this problem as well. For part A, the domain of this function is a little trickier because we have what's called a vertical asymptote at x equals 3, which means the function will you're never allowed to plug in x equals 3. So the domain of this function is all the x's. Because we have these arrows, we know that we're going to go from -infinity to 3, union, we take a break at 3, and then we go from 3 to infinity. So that's the domain. Our range of this function, we've got the arrows, so -infinity all the way up to this, what we call a horizontal asymptote, because it's never going to take on the value of 2. That's where this horizontal asymptote is. So we'll say -infinity to 2, union 2 to infinity. Okay, that was part A. Part B, this one's going to take us a little bit work on this one because we want to find the intercepts. And the intercepts, remember, an x-intercept you plug 0 in for y, and a y-intercept you plug 0 in for x. And unfortunately, it doesn't cross at an exact point, so we're going to have to find the equation of this line from -2, -3 to 2, 2, and then plug 0 in for y, and then plug 0 in for x, and find the corresponding intercepts. Now, it's actually easier on this graph. The intercepts they fall in exact points. We've got an x-intercept at 2, and we've got a y-intercept crossing also at 2. And I have made a mistake here on this range. I don't want to fix it. I don't want to go back and do the video again, so I'm going to have to fix this. I'm sorry. It's a little boo-boo. When I look at this problem, this is actually at y equals 3. It's not taking on any, it will never take on 3. So my eyes was drawn to that too, but that was this point right here. So sorry about that. This line right here is the line y equals 3. And that's the y value said it's never going to take on. So the range is -infinity to 3, union 3 to infinity. Sorry about that. Okay, because I knew that because the y-intercept is obviously that point at 0, 2. So that's y equals 2. Okay, back to this one. In order to find the x and y intercepts, we're going to have to find the equation of this line. We'll start by finding the slope. If we go from -3 to 2, that's going to be 5 units. And then -2 to 2 is 4. So our slope is +5/4. We can use either point to get the equation of the line. I'm going to use 2, 2 because I like to use positive points. So this is going to be y minus 2 equals 5/4 onto x minus 2. Now, to find the x-intercept, we'll put 0 in for y. So 0 minus 2 is equal to, let's see, this will be 5/4 x, and then we multiply 5/4 times 2. You think of this 2 over 1, and that's 10/4, or it's better thought of as 5 halves, because 2 goes into 4 2 times. So this is going to be minus 5 halves. And then we'll want to add 5 halves to this side. You can think of 2 as 4 halves. So -4 halves and +5 halves is 1/2 equal to 5/4 x. And then we can multiply by the reciprocal here, multiply by 4 over 5 on both sides, and we get 4/10 is equal to x. So our x-intercept is at about 4/10, which you can see that does look to be about the right place for your x-intercept. Now, and we can simplify 4/10, right? Because 2 divides into both of those, so that's actually at 2/5. Okay, now to find the y-intercept, you're going to plug 0 in for x in this equation. So I'm going to have to get some more room here. Let me come in here and get some more room. Oh, that didn't work. So taking our equation of our line, which was let me find it. Y minus 2 equals 5/4 x minus 2. So now I'm going to plug 0 in for x. So I'm going to have y minus 2 equals 5/4 times 0 minus 2. And so this is just going to simplify on that side. So this will be y minus 2 equals 2 goes into 4 2 times. So this is negative 5/2, right? Because you multiply. And then now I'll add 2 to both sides. Y equals negative 5/2 plus 2. Think of 2 as 4/2, which then negative 5 plus 4 is then a negative 1/2. So your y-intercept is negative 1/2. It's crossing out negative 1/2. Okay, let's see what else we need to find. Intervals on which the function is increasing, decreasing, and constant. So I'm going to just write it off to the side. This is increasing. Remember, you always give the x interval from -2 to 2. So we say -2 to 2. And constant, meaning that it always takes on the same y value. So it's constant over the x interval from 2 to 6. This one is... let's see, it's decreasing here, and then it's also decreasing here. So it's never increasing, it's decreasing from negative infinity. It's really decreasing throughout its domain. So negative infinity to 3, because we have a break there, union 3 to infinity, and it's never constant. Okay, neither of these functions has any type of symmetry. It doesn't have origin symmetry. It doesn't have y-axis symmetry. So both are neither even nor odd. You know, you can say when you put 2 in, you get 2. When you put -2 in, you get -3, which you have no type of symmetry. Here, when you put 2 in, you get 0. When you put -2 in, you get some number up here. So that's definitely no type of symmetry. So also neither even or odd. Okay. All right. So that was a fun little problem there. Okay, now this next problem is looking at what we call a piecewise defined function. Depending on what x value you have, you're going to have a different, you're going to choose one of 2 pieces. So for example, on this equation, if you want to know f at 1, you have to test the x value, whether x is less than 2 or whether x is greater than 2. Well, 1 is less than 2, so that means you're going to use this bottom equation. So f at 1 is just going to be 2. Now f at 2 is going to be, it's going to fall into this this top part of the graph, which is for x is greater than 2. When you get, you're going to do f at x equals x, and so you're going to plug 2 in there, and you're just going to get 2. F at 3 is going to be, all right, let's plug 3 in. Well, 3 is greater than 2, so we're going to use this equation again, and when that's true, when you have a value that's greater than 2, you say f of x equals x. So in this case, f of 3 will equal 3. So the graphs of these functions are kind of interesting because they're piecewise, so they can be in pieces. You want to kind of figure out this break point. When x is less than 2, this is telling us we're always going to have a y value of 2. So that's going to be a horizontal line always for any value to the left of 2. Now, when x is greater than or equal to 2, you get f of x. So it does turn out that when x is 2, you get 2. So we do have kind of like a closed dot. Sometimes you can have an open circle because there could be a jump, but in this one you don't. And then what might make sense is for you just to plop a few points in. When x is 3, f of x was also 3. When x was 4, you would get a value of 4. So you end up drawing that line y equals x, but only for x is greater than 2. So it's kind of an interesting function there. Okay, the next problem we're going to look at, or the next idea we're going to look at, is this idea of average rate of change, which is just a formula. It's on average what's happening to the graph over a particular interval. So you need to find f of b and then f of a, and then find their difference and then divide by b minus a. So on this function, f of b is going to be f of 2, which is 4 times 2 minus 9, or 8 minus 9, which is negative 1. And then f of a is f of negative 2, so that's going to be 4 times negative 2 minus 9, which is negative 8 minus 9, or negative 17. So the average rate of change, which is the formula f of b minus f of a divided by b minus a, is going to be equal to f of b, which was negative 1, minus f of a, which is negative 17, over b, which is 2, minus a, which is negative 2. And so this, how does this clean up? We'll make this a plus plus, and that's going to be 16 over 4. The average rate of change is 4. I'll tell you, this was a linear function, and the average rate of change ends up just being the slope of the secant line, but over the value. So in this case, because you're dealing with a line, it's just the slope of the line. But if you were dealing with a different type of equation, it wouldn't be just the slope of the line. Okay, another idea that you need for calculus is this idea of the difference quotient. And this is just some algebra practice. You are guaranteed a question like this on the final. They will absolutely give you a difference quotient question on the final. And so let's practice a few of these problems because they're kind of fun. All right, so the first thing what I would do is go ahead and compute f of x plus h. So what that means is you're going to put x plus h in for x in this equation. So it's going to be 3 times x plus h squared minus 2 times x plus h plus 5. All right, so this is 3 parenthesis x plus h times x plus h minus 2 times x plus h plus 5. Let's just clean this up. Remember, when you FOIL this out, you're going to have a middle term. So you're going to have 3 times x is x squared. You're going to have an xh and another xh, so you end up with 2 xh's plus h times h, which is h squared, minus 2x minus 2h, carefully distributing that negative sign, plus 5. And then finally, you could distribute the 3 through, and you get 3x squared plus 6xh plus 3h squared minus 2x minus 2h plus 5. So these problems, that's just f of x plus h. So the difference quotient is f of x plus h minus f of x all over h. And so you go ahead and write f of x plus h, which is this 3x squared plus 6xh plus 3h squared minus 2x minus 2h plus 5. Then you subtract what f of x is, which is this original function, 3x squared minus 2x plus 5, and you'll put that all over h. So then what you see here is that you have a 3x squared here that's minus a 3x squared, so that cancels. You have a minus 2x here, and then minus a negative 2x, so that's going to cancel. And then you have a 5 minus 5, which also cancels. So if you did this problem right, all you should remain with is stuff with an h in the numerator that you can factor out. Since the h is common to each term in the numerator, we can factor it out. We'll have h parentheses 6x plus 3h minus 2, and that's divided by h. And now when you have multiplication in your numerator, you can cancel if you have a factor in your denominator, which we do, so the h's cancel, and your final answer there for the difference quotient is 6x plus 3h minus 2. It's a very important idea for calculus. All right, now in this problem, it's a little bit, just a little bit of algebra to think about. F of x plus h is just going to be 1 over x plus h. So the difference quotient, which is f of x plus h minus f of x all over h, is going to be equal to f of x plus h, which is 1 over x plus h, minus f of x, which is 1 over x all over h. Now you'll have to get a common denominator here, which is going to be the product of these two denominators. So you'll multiply this by x over x and this one by x plus h over x plus h. So the common denominator in your numerator is the product x times x plus h. So this here is just going to be x minus x plus h, and you're going to be careful to put that in parentheses, over your common denominator, which is x times x plus h, and that's all over h. Okay, now x minus x, those cancel out. You're just left with an h in the numerator. So it's h over x times x plus h. You might remember when you're dividing by a fraction, it's the same as flipping and multiplying. So you can think of this as 1 over h. Then you can cancel, oops, I lost this negative. This is minus x minus h, so got a negative right there. You can cancel your h's, and you do get negative 1 over x times x plus h as your answer. So that is kind of a booger bear, that one. All right, last idea we want to talk about are these different types of transformations of functions. If you want to have a vertical shift, you add a value outside the function for a shift up and subtract it for a shift down. If you want to move it left or right, it's kind of the opposite. Within the function, you do a minus a particular value to go right and plus a particular value to go left. If you want an x-axis reflection, you reflect outside the function. If you want a y-axis reflection, you put the negative within the function itself. If you want stretching, vertical stretching or compressing, you put a number on the outside, and it will actually stretch just like you think. If it's greater than 1, it's going to be a stretch. If it's between 0 and 1, it's going to make it shorter. On horizontal stretching or compressing, it's kind of the opposite of what you would think. If you have a value between 0 and b, let's say the graph of y equals f of x is stretched away from the y-axis if your value is between 0 and 1, and it's compressed towards the y-axis if your value is greater than 1. Okay, so let's just do a couple of problems here. If we wanted to describe the transformations, remember this graph, the square root of x, is on your list of basic functions. We have adding 1 within the function and then minus 2 outside the function. So when you're within the function, it's always the opposite of what you think in the x direction. So that is going to be a shift left 1 unit and down 2 units. So A is going to be a horizontal shift left 1 unit, and down, or a vertical shift, 2 units. And then B is going to be a shift, in this case it'll be right 1 unit, and then up, so the plus 3 is going to be up 3 units. Okay, the cubic function, remember if you look on your sheet, the cubic function kind of looks like this. What's going to happen to the cubic function if you do these transformations? Well, this is going to shift it right 2 units because it's within the operation, and then up 1 unit. So you would take this shape and that little bend would go right 2, up 1. And then everything else would kind of look the same. It would just be shifted like that. Now on B, we've got a little bit more interest. We're going to go left 1 unit because it's plus within the operation, so it's always opposite. So it's going to be kind of opposite of what you would think to do. So you're going to do left 1 unit. You want to handle this reflection right here. That's a reflection across the x-axis. So you reflect it across the x-axis. And then you're going to go up 2 units. Okay? All right, if we wanted to graph these transformations, this is the absolute value function shifted right 1 unit. So we know the absolute value function originally looked like what? It looked like this. It was at 0, 0, and then at 1, 1, and then 2, 2, and then negative 1, 1, and then negative 2, 2. So originally it looked like this. That's just y equals the absolute value of x. Now, if you do absolute value of x plus 1, that is going to shift it to the left 1 unit. So this 0, 0 is going to become negative 1, 0. And then this negative 1, 1 is going to become negative 2, 1. And the 1, 1 becomes 0, 1. And so you get the idea that the whole graph is going to be shifted left 1 unit. Sorry, my pen didn't really work very well there, but it's going to be y. The red one here is y equals absolute value of x plus 1. Okay, this is going to take your original function, which I'll do in blue, which is your parent function is 1 over x, the basic function, which is called the reciprocal function. It looks like this. That's your graph of 1 over x. This is y equals 1 over x. Now, when you put this negative in front, it's going to reflect it across the x-axis. So I'll do that in red. It's going to look like this. It's going to be reflected across the x-axis. And everything else is going to be the same. You could always plot some points too if that made you feel better. So we just have a reflection. So this one went left 1, and this was an x-axis reflection. Okay, now here we have the graph of the absolute value of x. It's shifted 4 units to the right. So what will that look like? You'll have to do a minus 4 within the operation. It's stretched vertically by a factor of 2, so that means outside the operation you're going to have to put a 2. So, and then it's reflected about the x-axis, so we'll put a negative in front of the equation, and then shifted 3 units down, finally we'll just put minus 3. So we start here with x. If we want to shift it 4 units to the right, we're going to do a minus 4. If we want to stretch it vertically, we put by the factor, we put that on the outside. The reflect about the x-axis, we'll put a negative right out here. And then shifted down 3 units, we'll do minus 3. Okay? And then because I'm sure you guys are getting bored. I don't even know how many friends are still watching this. But I'll just do I'm just going to do one of these problems so you don't get too bored. What you're asked to do is take this graph already and think of it as a transformation where f of x plus 1. So g of x is equal to f of x plus 1. So what is that going to look like? Well, that just means you're going to take the original function and you're going to add 1 to all the y values. So instead of negative 4, negative 2, you're going to have negative 4, negative 1. Okay, instead of 1, 2, you're going to have 1, 3. Instead of 3, negative 1, you're going to have 3, 0. And instead of 5, 4, you'll have 5, 5. So somewhere up there. So every y coordinate got shifted up 1 unit. Okay, so that's just what that graph looks like. This is going to multiply each y by negative 2. Okay, now if you wanted to look at the absolute value of this function, what would happen is all the negative values would become positive. So on b, let's just do b for just this one. When you had -4 and -1, if you want to look at the absolute value of that, it's going to be -4 +1. And then you actually kind of need to figure out, it looks like somewhere between 1 to -3, -2 and -3, it changes. So you need to show that it's always going to be taking on positive values between -2 and -3 because it's an absolute value. Let's see if I can draw that a little bit better. It's going to take and then so what happens is this kind of, all of these negatives just kind of flip up here. And then the rest of the graph is going to look the same because that's the only part that was negative. So the rest of the graph is going to be the same. You had the 1, 3 here, and then coming down at 3, 0, and then that's all the same. So the absolute value, all it does is it makes that negative part positive. And so on 54, you could make the same kind of logic. So I have a boxer named Gus. So let's see who remembers that information. Who made it through the whole video? I don't know if that means that you did, but anyway, that's it. Bye.